Hey everyone, welcome back to our final talk of the symposium. Last but not least, we have Dr. Gillian Apps from the University of Texas at Austin with our talk, How Convection Churning Deep in the Earth's Mantle Impacts Surface Processes.
Thank you, Jay. Right, let me just get our pictures off here. There we go. Good morning, good afternoon, excuse me. I'm definitely dislocated here. I'm actually in England, but I'm speaking in my capacity as a researcher in Austin, in Texas. So this talk covers research I'm actively engaged in with my colleagues at the University of Texas in Austin and with Dr. Andy Pullum, an independent consultant. As you can see, I've lived in many parts of the world over my 40-year career, and I'm a geoscientist and started as a geophysicist with Shell in the North Sea. Thank you, Chris, for the intro to 3D seismic. I was one of those children playing with colored pencils way back when we did interpret seismic, 3D seismic on paper. And since then, I've worked in a number of tectonically active areas for BP, BHP, and ultimately returning to BP, ranging from basin scale play fairway analysis, whoops, a daisy, to core description for reservoir modeling. And now I'm at the University of Texas, and I work with the Applied Geodynamics Laboratory team at the Bureau of Economic Geology. And like many, I'm stepping away from hydrocarbon exploration towards finding good settings for carbon storage, applying skills I've learned over the years in the challenge of reversing or at least halting the rising Earth temperatures. But in everything I do, rocks are at the heart of my work. And I use geophysical, seismic, and well log data, but core and outcrop calibrate my thinking. So the talk I'm going to give today, which subject which Chris introduced very eloquently, is about the very largest scale phenomenon I've yet worked on, and yet it accounts for some of the very smallest observations I've made in the last decade in this thin section here. So good science is based on observation, but good prediction requires a great deal more than that. It also requires the understanding of mechanisms at work behind those observations and predictive models for what happen on continental margins, particularly in gravity tectonics and sediment interaction with growing structures, have been very important for hydrocarbon exploration, but are now being looked at through a different lens. For example, where will our human waste products end up? Trapped in the shallow waters where they can harm fish populations, or transported into deep water and buried rapidly? And today, I want to look at a driver that may account for a number of unexplained observations in the literature and provide a linking mechanism between two apparently completely unrelated phenomena on continental margins: dramatic changes in gravity-driven tectonics and the existence of very large deep water sandy fans. And that driver may be mantle-driven topography. So why should we care about processes that occur deep beneath the Earth's surface? Well, for many reasons. As Dave McNamara said yesterday, geothermal energy is set to become an increasingly important component of renewable sustainable energy sources, even in England. But with respect to what I've come to talk about today, I'm going to look at these three questions. How does topography develop on the Earth's surface? Are there deep-seated processes that may fundamentally change what type of sediment is eroded from uplifted areas and where that sediment ends up? And what happens when slopes increase just a little bit over very large distances? And the example I have put here is actually the Storegga slide, which was not related to dynamic topography, but it was ultimately linked, or has been linked, back to post-glacial isostatic rebound. But the scale of the tsunami that was caused by that slide, plus the retrogressive failures afterwards, immediately afterwards, we see the tsunami record actually on the east coast of England. So let's start with the Earth's topography. So if you just take a look at this map, the astute amongst you may actually notice that sea level is not where it is present day. This map was actually drawn for a course in sustainable science and is drawn at the 200-meter sea level rise, assuming all land glaciers have melted. But what you will see is that the darker colors are the oceans, and the lighter colors in the reds, yellows, and that pale green and blue are the continents. And the first order Earth topography effect is density. The oceanic crust is largely basaltic and it's dense, and the continents are granitic dominantly, although have many other things in them, but they're less dense. And therefore, through Eistasy, they are higher. The second question, the sediment journey from source to sink. Let's look today at, are there deep-seated processes that may fundamentally change what type of sediment is eroded and where it ends up. At the present day, we see sediment stored in every part of the environment spectrum over much of the planet. But there are times in Earth history when sediment is eroded from the mountains and stripped from the fluvial plains and ends up, and the shallow marine environments, and ends up bringing sand, silt, and mud directly into the deep water to form huge deep water sandy fans deposited hundreds of miles from the time equivalent shoreline. And I'm going to look at one of these times on the North American continent in the Miocene, when turbidity currents carried huge volumes of material quickly and efficiently to the deep water Gulf of Mexico. So what are turbidity currents? There are those of you in the audience who may not be familiar with turbidity currents. And here are 3 videos that actually give you an illustration of turbidity currents, which are a specialized type of density current where energy and momentum of the flow is actually created by a fluid sediment mix that is denser than the ambient fluid, be it air or water. So in the case of the snow avalanche, it's snow mixing with air. In the case of the turbidity currents in this experiment and here in the Monterey Canyon, it's actually sediment that's mixed with water, and in this case, seawater. And as you can see, they move pretty jolly fast. So natural examples in the subaerial environment are avalanches and also include pyroclastic ignimbrite flows. And you can see in this avalanche generated turbidity current on the left, the mixture of snow and air, that they have tremendous energy, traveling fast with momentum to ride high up on the valley side here. But in the deep water, they can also travel very far, hundreds of miles from the shelf margins, where failure actually gives rise to these very large turbidity currents entering the deep water slopes. So thirdly, gravity tectonics on continental margins. I'm going to look particularly at continental margins that have a mobile substrate within the sediment package. And this example is from the Gulf of Mexico, where the red is salt, which is a mobile substrate and behaves over geological time like a fluid, a fairly stiff fluid, but still a fluid. And when you tilt the margin, things happen, which I will take a look at later. So going back to our first question, what causes topographic highs? Well, we looked at density, but also most of us in geology learn very early that when you thicken crust, for example, in mountain belts, the isostasy actually causes the mountains to form. So basically you thicken the crust and it is supported on the buoyant mantle, and the continental crust, the thickened crust, actually rises higher, for example, in the Alps and in Everest. Just like this iceberg here, they have deep roots, but they rise high above the Earth's surface. And the second example I'm going to look at, which Janine knows a great deal more about than I do, are supervolcanoes. And supervolcanoes make significant topography, both in the oceans and on land. And I'm just going to show, wait till the map comes up that the National Geographic have provided us here, and say that a lot of those supervolcanoes are a direct result of plate tectonics, for example, subduction. So these down here, for example, and all the way around the Western Pacific are largely related to plate tectonics. But there's one in here, which I'm going to come back to, which is Yellowstone, and that is a massive supervolcano, which has been active since the mid-Miocene. And that is a supervolcano that is also a hotspot. And supervolcanoes that are hotspots are caused by mantle circulation, which I'm going to come to now. So, in talking about hotspots, it brings us very nicely to the topic of dynamic topography driven by mantle circulation. This is a geoid, and it represents the effect of Earth's gravitational field. So it includes many factors, for example, crustal density, but a significant component of the long wavelength gravity field reflects mantle circulation, with positive gravity anomalies above areas upwarped by a mantle plume, here in red, and downwarped when the crust is warped down above a downwelling mantle, here in blue. Circulation in the mantle occurs at many different levels. Not all the cells penetrate deep into the mantle like the major hotspots, and the circulation patterns change through time. Therefore, not all upwellings are coincident with the deeper seated hotspots. They may coincide at some points in space and time, and we'll look at one of those, but not necessarily. So for those of you who, like me, needed or would appreciate a refresher on the Earth's structure, the Earth is divided into crust, mantle, and core based on composition. However, there's an equally important division based on mechanical properties: the lithosphere, the asthenosphere, and the mesosphere. Gosh, tongue twisters. The outer core boundary is the same in both cases. The lithosphere, I can't get my words out today. The lithosphere is solid, strong, and brittle, and includes the upper part of the mantle, and it's the movement of the lithosphere that makes plate tectonics. The asthenosphere is still solid, but it's significantly weaker and relatively low viscosity, and that's important. And the mantle beneath is somewhat stiffer, but behaves over long periods of time like a fluid. The important consequence of the asthenosphere's weakness for our purposes is that this weak asthenosphere is the layer in which much of mantle flow occurs. Hotspots are deeper seated, here, and longer lasting, hundreds of millions of years, whereas upper mantle circulation cells appear to be shorter lived. So let's focus on the upper mantle circulation patterns for a minute. These patterns vary spatially and through time, from symmetrical to asymmetric configuration, with potentially multiple sources of heat establishing extensive channels of hot, buoyant, low viscosity fluids near the surface, as shown here in the figure by Tobias Hoink et al. And Bernardic. The most recent research coming from Fred Richards' PhD under Nicky White at Cambridge would suggest that low viscosity channels, approximately 100 to 150 kilometers thick, exist in the upper 300 kilometers of the asthenosphere and are largely responsible for most of the Earth's dynamic topography. The transition to cold downwarp might be quite abrupt, with implications for surface gradient at that transition, which we'll come back to in respect to the Gulf of Mexico, if I remember. The downwarps could be smaller and higher relief, while the uplifted areas could be very broad. Remember that when we talk about the American continent and the Gulf of Mexico shelf margin. And a figure from Richard's paper shows that at present day, the seismic velocity variations here on the left, that are the proxy for mantle flow are spatially very variable. The western flank of the South Atlantic has broad asymmetric pattern here, whereas the eastern flank has a higher spatial variation and more symmetric too. Let's go to the diagram on the right here. Madison East, at the University of Sydney, demonstrated that mantle circulation has also changed dramatically through time, with whole mantle overturn alternating with times when upper mantle flow dominates, which is probably characteristic of present day. I love that diagram. So let's look at Mark Hoggard's 2016 paper, where he established that at present day, the peak amplitudes of upper mantle circulation were in the order of 1 kilometre, with wavelengths of over 1,000 kilometres. And the current evidence would suggest that the signal of that scale of a senospheric overturn is transient on the order of 1 to 10 millennia timescale, which, for those of you interested in sequence stratigraphy, would be a third order sequence. I'll come back to that too. So the method he used to calculate the component of surface topography due to mantle circulation is easily demonstrated in the oceans at present day. Most of you at university doing earth sciences already know that new crust is generated at mid-oceanic ridges here. And as the magma cools, two things happen. First, the crust records the magnetic field of the Earth at the point where the magma solidifies. And so each increment of new crust records progressively the polar reversals through time, like a tape recorder. And the second thing that happens is that as the basalt cools, it sinks in a predictable fashion through time, here. And it was Dan Mackenzie and his team at Cambridge, way back in the late 70s, who established this. The water-loaded depth, if you take the water-loaded depth of the oceanic crust, removing the effect of sediment loading, and then subtract the predicted depth calculated from the age of the oceanic crust derived from the magnetic stripes, you often get a residual topography. And that residual topography is mantle-driven topography. And we have an example here on the west side of the Indian continent, where the mantle-driven topography gives rise to a positive anomaly. And here on the east side of the Indian continent, an example where the negative downwarp causes a significant depression of the Earth's crust. On the continents, establishing the component of topography generated by dynamic topography is a lot more challenging. There are so many factors involved in generating topographic elevation, as I've shown you, crustal thickening, density, etc. However, if we take the Colorado Plateau as an example, then wide-angle seismic surveys which penetrate deep through the crust and image the crust mantle boundary, and the receiver functions of very far-traveled natural seismic waves, which again penetrate deep beneath the crust, have demonstrated that the crust of the Colorado Plateau is thinner than or equal to, but a lot of it is thinner than the crust beneath the Great Plains, even though it is topographically elevated on average at least a mile above sea level, much higher than the Great Plains. The region is associated with long wavelength gravity anomaly, and tomographic models suggest that the region is supported by upwelling hotter mantle. The timing of the uplift may be constrained a number of different ways, but as Chris Jackson showed us earlier, the most complete record is actually preserved in long river profiles. Gareth Roberts' breakthrough paper in 2012 was the one that established the method of inverting uplift topography uplift history, from the fluvial nick point migration. And here is a classic nick point in a river that we all know and love at the Niagara Falls. And the longest rivers preserve the greatest uplift history back to the Cretaceous. I'm not going to go into the method in detail, and I would encourage you to follow up with Gareth Roberts, who is now at Imperial College London, for more details. Specifically, it does require a lot of river profiles to be analysed, not just one, because obviously other factors do figure into how fast nick points migrate and where exactly the uplift occurs. So you really want as many as possible on your uplifted area. So another thing I want to point out is that the effect of dynamic topography on surface elevation is one thing, but if you want to understand the subsurface and the slope on the basement or within the crust itself, then it can be actually enhanced by erosion, where the dynamic uplift is onshore, and by sediment loading in regions of downwarp, particularly where the sediment load is offshore, on continental margins where you have huge thicknesses of sediment. And a positive feedback can be established, increasing the basement gradient and all other subsurface gradients between the source and sink over time. And I want to look at this effect on two continental margins, each with paired uplift onshore and downwarp offshore. I'm going to look at Angola and the Gulf of Mexico. And first, I'm going to look at the effect on gravity tectonics and actually on salt tectonics, and then I'll look at the response of depositional systems. So let's look at the response of gravity tectonics and salt. First, I'm going to look at the slope controls on the rate of salt movement in Kwanzaa, and particularly the development of growth faults offshore Kwanzaa. And then I'm going to look at where and when to expect extension and compression in the Gulf of Mexico. Extension and contraction, in fact. Okay, so this west-east cross-section through the Kwanzaa passive margin shows truncation here, onshore, and all the way into the shelf of all the pre-Miocene strata, showing that the onshore area and the shelf have been uplifted. And then a little further offshore, what you see is a bunch of growth faults here, recording the sliding and spreading of the material down the slope and into the deep water. The extensional growth fault history in the slope was actually documented by Mike Hudek and Martin Jackson in two papers. And they demonstrated that although the Miocene uplift here was only a matter of a few hundred meters on the shelf, the rate of downslope translation recorded in those growth faults was actually enormously fast. So it went from 300 meters per million years to 3,200 meters per million years. That's a tenfold increase. So why? Well, it all comes down to the salt that underlies here. Now, in this particular cross-section, salt is in blue. And there was salt at the time underneath this whole area here, which is now concentrated actually in the deep water. Salt is a viscous fluid. In other words, when you hit it hard and the deformation rate is fast, then it behaves brittly. But if you deform it slowly over time, then it actually behaves as a fluid. And if you increase the strain rate, it's directly proportional to the stress you apply to it. If you increase the gradient, you increase the stress experienced by the sediment wedge, which is sat on top of the salt, and the sediment wedge is undergoing gravity failure. The salt begins to move faster when the slope is increased. So what caused the slope to increase and that tenfold increase in the rate of downslope translation? As Mike Hudek and Martin Jackson said, there's no plate tectonic reason to account for this uplift. There are a number of different theories, and Michael Giraud actually proposed rift shoulder uplift in 2010, but the timing is wrong. The rifting on this margin actually occurred dominantly in the Cretaceous, and this is actually Miocene uplift. However, the map is really useful because it shows that the drainage is actually radial around a pretty much circular Bie Dome. It took until 2014 for Jonathan Paul to make sense of the dynamic topographic patterns that support onshore Africa. And he was able to show the Bie Dome as a prominent upwarp area. And there is a corresponding map offshore produced by Hoggard, which shows the corresponding downwarp. So you have upwarp on the Bie Dome here and downwarp offshore. And the history of this uplift? Well, Jonathan inverted the uplift history from the fluvial profiles all the way around the Bie Dome and was able to show that there was a rapid rate of rise in the mid-Miocene, which would be coincident with the accelerated downslope translation on the slope documented by Mike Hudek and Martin Jackson. So that was Angola, with upwarp onshore on the Bie Dome and corresponding downwarp offshore. The increase in the slope was likely to be about 0.5 degree, and yet it caused a 10-fold increase in the downslope translation. And there was a large-scale redistribution of sediment load into the deep water from the shelf margin too. Now let's go to the Gulf of Mexico, where the upwarp onshore is in the west or northwest, and the downwarp offshore is in the Gulf of Mexico itself to the southeast, with a similar increase in source to sink gradient. The upwarp onshore is the Colorado Plateau here, and Gareth Roberts established the history of that uplift with two distinct phases of uplift. One through the late Cretaceous and into the Paleocene, and the second at the Oligocene and into the Miocene. Independently supported by fish and track data and also geomorphological evidence. And Mark Hoggard, in his oceanic analysis, has shown that there is a corresponding downwarp in the Gulf of Mexico. Now, the downwarp is partly driven by tectonics of the flexure due to the tectonics in Mexico. However, it is extreme and it's very much centered in this central area here in the Gulf of Mexico. Given the pairing of the dynamic topography onshore, it is very likely that the history of this downwarp is very similar to the history of the upwarp. The first phase of dynamic uplift in the Colorado Plateau is coincident with the Lauramide orogeny, but affects a much broader area. And Ron Blakey's map shows the Upper Cretaceous fallen basin to the severe orogeny here was uplifted above sea level over the entire plateau area here. And two major drainage systems were established, completely new, one going northwards into the Boreal Ocean and one going southwards into the Gulf of Mexico. And they persist to the present day. So what happens offshore? Well, the first thing to note are the very large-scale gravity failure systems here, routing all the way down to the Luan Salt. And these large, and to a Mesozoic canopy actually, and the large extensional gaps that opened up near the shelf edge were filled with Paleocene and Eocene sediment, like this one documented by Carl Taddeucci and Mark Rowan and their co-authors. And the corresponding down-dip compressional belts are observed to deform Upper Cretaceous strata here in the ultra-deep water Gulf of Mexico, and those folds are filled, the topography of those folds are filled with Paleocene sediment. At this time, large areas of the lower slope canopy also shows salt inflation. In other words, both the salt and the sediment are moving whole scale downslope. Moving on to the Miocene, and the second phase of rapid uplift here, in yellow, this big star here. The first thing to note is a similarity with the Kwanzaa section that we showed you, with erosion of all the pre-Miocene strata on this seismic line shown here, and a huge growth wedge of Miocene sediment and post-Miocene sediment expanding offshore. The unconformity is beautifully illustrated in the subcrop map on Texas geology, but it extends into the seismic section here on the shelf, published by Tim Dooley. So what do you see? Well, Tim Dooley published a fantastic piece of experiment, which is one of his sandbox experiments, where he put a prograding wedge of sediment, just like we see, shelf, prograding slope, toe of slope into the abyssal plain here, all sat on top of a deep layer of salt. And what you see when it's just a stable prograding wedge is, or not particularly stable, but what you see when it's a normal prograding wedge and you're not tilting it, is you see extension at the shelf margin here, and you see a corresponding shortening of the sediment pile at the distal salt pinch out at the base of slope. What he then did was tilt the entire rig, which is no mean feat, scrape off the equivalent of the shelf area and erode it, mimicking that unconformity we saw. So he tilted his rig, and what he saw was that the extension jumped back into the shelf, and the zone of compression expanded away from the toe of slope. And note too, he also saw a thickening of the salt, very much like we did in the Paleocene. Why does this happen? Well, I've mentioned before that salt is viscous. So another property of salt, it not only, the strain rate is proportional to the stress applied, and the strength is also rate limited. So if we take the first situation where we have just a prograding margin and no tilting, then what we see is extension at the shelf margin, we see translation of the slope, and we see contraction at the toe of slope. And the failure is limited by the strength of the wedge. If you push this with active dynamic topography, uplift onshore, downwarp offshore, into a really fast, far from equilibrium situation, then the failure is limited by the viscous resistance of that salt detachment. So what you get is effectively a car crash situation where the toe of slope, contraction begins at the toe of slope and then spreads back up slope as the fastest rate of movement of material in the greatest slope area here collides progressively with the slower moving pieces of the contracting slope in the toe of slope where the slope is lower. So the contraction migrates back up slope away from that toe of slope. So salt is a viscous detachment and strain rate is proportional to stress. Gravity failure speeds up and the distribution of extension and compression changes in the deforming wedge quite rapidly. So let's go on now to look at the redistribution of sediment load to the ultra deep water. And that, as we have pointed out, actually exacerbates the subsurface tilt. And so you can imagine where this is going. I'm going to look at the impact of dynamic topography on increasing the source gradient from source to sink. And I'm also going to look at the associated volcanism seen in the upwarp domain. I'm going to look at the effect of that topography on sediment flux, slope stability, and also reservoir quality. As I said, dynamic topography affects the very smallest things I've ever observed. And I'm going to look at two examples, one in the Paleogene and one in the Middle Miocene, and both of them will come from the Gulf of Mexico. So we understand the sediment provenance areas. We know a great deal about sediment provenance for the Gulf of Mexico from studies over decades, and a lot of them by Bill Galloway, an absolute master of the subject. And until recently, we looked primarily at the plate tectonic sources. We looked at the Laramide orogenies, we looked at the Mexican sources due to the Mexican orogenies. But if you add dynamic topography, it explains some of the other source areas that become active. On Gareth Roberts' map, his area of the Colorado Plateau, there was also another area associated with the Appalachians. And in fact, in the Miocene, the Mississippi is shedding material from a rejuvenated Appalachian source area, which I will not actually return to in detail because I'm not an Appalachian expert, but I would say that the breadth of the areas that source the Mississippi would be explained by adding the dynamic component to the plate tectonic component. So what are the effects in the Gulf of Mexico? This is a chronostratigraphic diagram, which means that I've plotted lithology in time, not in thickness. So if you look at this in the Gulf of Mexico, what you see dominantly in the Mesozoic is you see carbonates in the Gulf of Mexico. Well, the reason for that is because all the clastic sediment is caught up in the severe foreland basin that I showed you earlier on Ron Blakey's Cretaceous map. And you don't really have sediment shedding into the Gulf of Mexico except on very rare occasions like the Tuscaloosa here in the lower Cretaceous. However, what happens in that first phase of dynamic topographic uplift in the late Cretaceous and at the Paleocene boundary is what you see is suddenly the whole world changes in the Gulf of Mexico. From then on, you have clastic sediment shed lock, stock and barrel into the deep water. And what you see is the fastest and most clastic sediment is actually shed during the two periods of dynamic topographic uplift. One in the Paleocene, which deposits what we call Wilcox reservoirs, and the second in the Miocene, which is responsible for some of the biggest fields in the Gulf of Mexico, oil fields that is, like Thunder Horse and Atlantis and Mad Dog. So the rates of sediment flux in the Paleocene into the deep water are astonishing. In fact, they reach sediment flux rates equivalent to the Pleistocene. Of course, the Pleistocene is glacial, static driven, but you get equivalent sediment flux in the Paleocene. Huge volumes of sediment shed from the continent of America from newly emerging terrains, plus reactivated older ones into the Gulf. As I say, some of those older ones have no tectonic reason for uplift. What happens in that second phase is even more interesting, or at least we've got a better record of it, should we say. We've studied it more. So this little GIF at the bottom here shows a prograding margin, and it's replaying over several periods of time. So let's start at the beginning. You see a prograding margin, which is tilted and then collapses. And you see deep water sediment being deposited on top of the yellow shelf margin and delta material from the shelf. So what happened in the Miocene? Well, this map here shows Mark Edwards' mapping of huge laterally extensive shelf margin failures, big submarine gravity failures. So if you take the Storaga slide, which is about 100 miles across. This one here, for example, which is in the mid-Miocene and is called the Pontchartrain, well, it also includes the harangue, is actually over 300 miles long. It's not saying it's a single event, but these events happened in a very short space of time. It unzippered the whole of the shelf margin, which was actively receiving sediment at the time. So what do we see in these failure complexes? We see on the seismic, we see rotated blocks of failed shelfal material. Well, we see shelfal and deltaic material sliding down the slope. So we see the extensional domain of those gravity failures. On top of that, immediately above it, we see what are called or termed bathyal wedges. Well, they were described first in the 40s by David Pope and his co-author Smith. I don't actually know Smith's Christian name. If you unpack them carefully, what you see is that these bathyal wedges correlate up dip to an unconformity. They do not correlate to a transgressive systems track. They are not floods in the classic sequence stratigraphic sense of the term, and they actually cause quite a bit of confusion between Galloway and Vail. These bathyal wedges were interpreted for a long time as flood-related transgressive wedges, but they're not, because there is an unconformity equivalent to these bathyal wedges. There is no time equivalent sediment up dip at all, and they are sat directly on top of these failed shelf margins. They contain dominantly mud rock, and the mud rock is odd. It's very highly pressured, and it's really difficult to drill through, and it also contains turbidites, thin turbidites, but it also, most importantly, is full of agglutinated forams, and these forams are characteristic of very stressed environments, particularly highly turbulent environments. So I think you can see where this is headed. Right, so what we believe is going on is that these shelf margin wedges, these bathyal wedges, actually represent something super important. And it was Andy Pulham who did the time correlation of the bathyal wedges here in red on this chronostrat here to the time equivalent log signatures in the deep water. And what you see is that the time equivalent deep water contains all the best reservoir sands. So the lower and middle Miocene reservoirs are time equivalent to the bathyal wedge fill in the up dip area. So that turbulent mud rock that you see up dip is the suspended sediment thrown into suspension by the collapse of the margin, and then what I'm going to describe now, the subsequent release of thousands of turbidity currents into the ultra deep water through that steep head of the canyon, the steep shelf margin failure wall at the back. So what we believe, or what Andy Pulham actually published with Trevor Elliott, he spoke about at the GCS of CPM back in 2014, is what they think that happens is that the shelf margin failure itself actually generates a big mega turbidity current in the deep water and leaves a big evacuated surface back at the shelf margin with steep scars. Those steep scars rebound due to isostasy and the fluvial systems incise into them. If you then combine that with the dynamic topographic uplift that I'm talking about in the Colorado Plateau, then what I think is happening is that you get a flushing of the fluvial systems directly out into the deep water. It takes a long while to heal those scars. And while it's being healed, then you get big turbidity currents released into the deep water, which leave little remnants of themselves in a bypass facies up in the bathyal wedge, that's those thin turbidites, but deposit the huge deep water sediments out in the ultra deep water, hundreds of miles from the shelf margin, that we know and love as deep water reservoirs for hydrocarbons and gas. What else happens? Well, something really quite scary for all the mammals onshore that we were talking about earlier today. And that is that because of that dynamic uplift, the mantle upwelling also causes and gives rise to lots of melt. So what you see, coincident with particularly this second phase of uplift and even into the present day, is a lot of volcanic activity. And the most active of them is the Yellowstone in the Miocene. The Yellowstone is actually a very deep-seated hotspot, and it's still active today. Well, it's actually quiet at the moment, but it's due to come and be another massive supervolcanic eruption just about now, really. But when that volcano went off, and it did so multiple times in the Middle Miocene, it killed pretty much everything in the ash path, and most of the mammals onshore died. And that in itself is a pretty dramatic story. But the other interesting thing is that that ash was deposited on shore, and we do see the ash on shore, but it was also choked up all the fluvial systems. And with the dynamic topography that we're seeing, those fluvial systems were flushed out into the shelf margin, coeval shelf margin, and straight out into the deep water. And what we see are thick, redeposited volcanic ash, complete with all the shards, the glass shards, even with the little tricorn vesicule remnants. So turbidity currents, although they're extraordinarily energetic, are not very aggressive in terms of abrading the sediment, because the sediment is kept in turbulence and doesn't spend much time on the seabed until it's deposited. And when I say thick, I mean thick. That's 100 feet of almost pure redeposited ash in the Middle Miocene for this Cougar Point ash. So that's the Gulf of Mexico. But if I go back to what the diagram right at the beginning of my talk, as Chris Jackson told us, so we come full circle back to this early afternoon's talk, what about that North Sea Tertiary example? Well, he showed us the Paleocene, he showed us actually a Holocene eroded topography, subaerial eroded topography in the North Sea. But the Iceland plume began its activity initiated during the Paleogene, and there are equivalent Eocene map topographies that have been analysed by, again, the Bullard Labs in Cambridge and published upon. But what you see in the North Sea is bypass fans that are detached from their time equivalent shelf, and probably via a similar mechanism to the Gulf of Mexico, you see huge, huge deep water sandy fans shed again, almost certainly off that topographically uplifted area related to the Iceland plume and straight out into deep water. So dynamic topography has dramatic and predictable effects. You see step changes in salt tectonic processes and rates, and dramatic changes in sediment flux to the continental margins, affecting shelf margin stability, and deep water systems can all be directly related to large 1,000-kilometer scale gradient changes of relatively small amounts accentuated by erosion and deposition, working in unison to create subsurface dips that are greater, and facilitated by mobile substrates like salt and mud. It's no surprise that the changing the regional gradient, even by a relatively small amount, has a profound effect. And we've only recently begun to understand the full implications of dynamic topography, but it's mappable in space and through time, at least as far back as the Cretaceous. Difficult to get longer river profiles, but we're now working in the subsurface as well. My personal prejudice is that it is one, if not the, principal driver for second and third order sequence boundaries. And in the Gulf of Mexico, it's responsible for the first order change from carbonate deposition to clastic deposition. And thank you for your attention. Right, I might as well stop sharing and I'll take questions now. Wait a minute, no, I won't quite stop sharing because I want to acknowledge both Professor Nikki White and the team at the Bullard Labs and anyone who's doing and publishing research, but particularly these guys, because they were the ones who first put me onto it. Gareth Roberts was one of those, and he's now at Imperial College. And my co-authors and other talks I've given on this subject, Andy Pullum, Tim Dooley, who I work with at the AGL, and Alex Bump, who I worked with in BP and is now also at the BEG. And Frank Peel, who did quite a lot of the graphics for my talk. Thank you.
Thank you, Gillian, for such an interesting talk. And thank you for joining us this weekend for our symposium. It's been absolutely lovely having you. We now have some time for some questions from the Discord and Zoom. So the first one we can see is, due to the transient or incomplete nature of the effects of dynamic topography in the geological record, are there any difficulties in using geological observations to constrain the Earth's paleo-mantle dynamics and linkages to large-scale surface processes?
Yes, actually, it is challenging. And I received quite a lot of pushback on these mechanisms, but that's why I specifically chose areas where you can't add in a tectonic component, like the Bie Dome. It sat there as an unexplained phenomenon that operated in the Miocene, and then this inversion of fluvial profiles. And please go to Gareth Roberts if you want to know the details of the methodology, because it is mathematically important that it's a statistically valid process that you can apply Bayesian statistics to. But yes, it is difficult to deconvolve, and particularly in the Gulf of Mexico, because we have so much tectonics going on with Mexico going up related to huge amounts of active compression belt, mountain belt building. It can be very difficult to deconvolve the two. But the thing that I would draw attention to is the sheer scale of dynamic topography. This is not something that goes on at the 100-kilometer scale. This is 1,000-kilometer scale plus. So I think that wavelength is really critical. So when people call attention to mantle-driven dynamic topography, you're not looking at the scale that often plate tectonics operates at, rifting and mountain belt building particularly. Flexure, slightly different matter, but certainly when I'm looking at that Mississippi drainage area, there are parts of that I just can't apply a tectonic process to explain. But yes, it's non-trivial. And of course, it's difficult to do further back than you have a long river profile to establish that history. Again, details, go to Imperial or to the Bullard Labs in the UK, and there are other people working on this abroad too.
Okay, we've got a few questions in the Zoom chat as well as the Discord. So our first one says, fabulous talk. Is the outcrop of older rocks in central Texas the expression of the uplift discussed in the slope dynamics?
Yeah, absolutely. So that tilt is very much like the one you see off the Bie Dome, and you can see the scale of it. I mean, it affects the whole of Texas. It goes into Louisiana as well, but it's so beautiful, that subcrop map. Yes, that is the expression of it. And actually, interestingly, there is a Paleocene expression of it, but it hasn't been as well mapped because it's I was just about to swear, it's so much deeper because the Miocene and post-Miocene sediment load on the Gulf of Mexico shelf and shelf margin is humongous, particularly the Pleistocene one. Yeah, carry on. So yes, that is it.
There's another one in the Zoom. It's quite a long one, so I'll try and process it. It says, interesting talk and great to see this process getting more attention. Uplift, subsidence, and tilting require changes in dynamic topography. So do you think the events you are describing, several of which incidentally were first documented in forward models back in the mid-1990s, are caused by very dynamic upper mantle flow or by movement of tectonic plates over a more static mantle thermal structure, or perhaps a mixture of both?
Yeah, definitely a mixture of both, Pete. So in fact, even with that Colorado Plateau one, Yellowstone is static. It's a deep seated one, and the plate is migrating over it. And the Snake River is the record of a series of explosive caldera sites that have been linked up by the Snake River. Terrifying, actually. Because if you look at it and you actually map the timing of it, the temporal frequency of Yellowstone, it's really ready to go now. But so that particular component is, you can see the migration of the continent over that deep one. But the shallower ones, interesting. Again, we really need a plate tectonic expert in the room, who anyone's present very willing to or able to contribute to this discussion, because that there is an interplay between the plate tectonics, the subduction and the detachment of the subducting plate and the generation of the shallow level asthenospheric channels in the laramide. And the Fralin plate gets detached, and that ends up going really quite deep into the mantle, and that almost certainly is one of the reasons that you get this overturn set up in the when the laramide kicks off, and that overturn is probably phased. So a mixture of both, Pete. Happy to talk about it anytime.
Okay, I think we've got time for one more question, so I'll take this one from the Discord. It says, great talk, so much content. Considering the long timescales of dynamic topography, do ice sheets with 1,000-year timescales suppress or enhance these effects, or perhaps both?
Oh, super question. Absolutely brilliant question. And in fact, I really want to talk to that wonderful reference that Chris came up with. Her name is Gaia, or his name, but I assume it's a lady, Gaia Stuckey-Decay. What a brilliant name. Because she may well know the answer to this, because when you actually look at the UK, everyone attributes, or a lot of people attribute, the isostatic rebound. And I know in both the UK and northern UK and Norway, we had, 7 kilometers of ice. So that's a serious amount of isostatic rebound you get when you melt that. But that is going on in conjunction with Iceland being a mega superplume. So I'm interested in the answer to that question, because my husband and I are both looking at Pleistocene age mud withdrawal basins, and we wonder what triggered the mobility of the mud in the lower Pleistocene. So what I would which was a warm period before the big ice age set off. Well, I'd be really interested to know whether that was the Iceland plume. And I think even now, what component of the tilt is actually related to that. Oh, I'm not sure whether that answered the question, but I would definitely say, again, it's like a seismic wave. You've got to deconvolve all the different parameters that go into producing the final topographic effect.